KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Free bus for LKG to 8th standard.
Free, hygienic and nutritious food.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Education Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we are going to discuss about polarization by reflection, right? Polarization by reflection, okay ma? Right. In our previous class, we concentrated on polarization by scattering. Polarization by scattering, right? So what is scattering? When a light is going to scattered, so in a scattered light, when compared to the incident light, in a scattered light, so what about the polarization? So what about the electric component of vectors? So that we are going to represent, that is what the situation. What about that how a light is going to polarized? That is going to represent by using arrows and dots, right? So this situation, so when a light is going to scatter, what happens to the scattered light when compared to the incident sunlight or unpolarized light? We discussed in our last class clearly. But in this class, our focus is to discuss about polarization by reflection, right? So if a light is going to reflect, what happens to the light? Regarding polarization. Similarly, here in this picture, you can also see the refracted ray. It is what? It is water medium, it is air medium, it is the incident light, that is what? Unpolarized light. And polarized light, it is a reflected light. It is a reflected light. You know very well, when a light is going to incident, when a light is going to meet a medium, because of the medium molecules, because of the difference in optical density, certain amount of energy is going to reflect and certain amount of energy is going to refract. But our more concentration is about reflection, but at the same time we are also seeing refraction, right? See here. So if you observe carefully here, in this picture, a light reflected from a transparent medium. It is what? A transparent medium. Light reflected from a transparent medium, here water, right? So we know that the dots and arrows and dots, see here ma, see observe the light, arrows and dots, not only here, here and here also. So the dots and arrows indicates that both polarizations are present in the incident and refracted waves. See, this is the refracted waves, here we have arrows and dots, this is the incident wave, here also we have arrows and dots. So these dots and arrows indicate that both polarizations are present, okay, right. And here we drawn a situation where the reflected wave travels at right angles to the refracted wave. So the angle between these two is 90 degrees. You just keep in mind, here the situation is the angle between reflected and refracted wave is 90 degrees, right. So when the oscillating electrons in the water produce the reflected wave, see, when incident light is going to meet the molecules of water, right, the oscillating electrons in the water produce the reflected wave. Observe carefully, the oscillating, right, the oscillating electrons in the water produce the reflected wave. These, so whatever the these move in the two directions, transfers to the radiation from the wave in the medium. I will repeat once again. First I told you the oscillating, when an incident light meets the surface, that is what the water molecules, meets the water molecules, the oscillating electrons present in the water molecules produce reflected wave. And then next, these move in the two directions. In the two directions, transverse to the radiation from the wave in the medium. Transverse to the radiation from the wave in the medium, that is refracted wave. That is refracted wave. So before this reflection and refraction, first the incident light is going to meet the water molecules. So in the water molecules there are oscillating electrons, right? Next, the arrows are parallel to the direction of the reflected wave. The arrows are parallel to the direction of the reflected wave, right? Next, motion in this direction does not contribute to the reflected wave, right? So whatever motion which constitutes does not contribute to the reflected wave, right? Next, if you see here in this picture, you can observe what is the incident wave, what is the reflected wave, and what is the refracted wave, right? So here the reflected light is linearly polarized. Reflected light is linearly polarized, perpendicular to the plane of the figure. Perpendicular to the plane of the figure, right? So I will repeat once again. Reflected light is therefore linearly polarized, perpendicular to the plane of the figure, means here plane of the board, perpendicular to the plane of the board. Okay, right. And you can also check this. You can also check this like when we are doing some experiment like that situation. You can also check this. That is what? By using analyzer. So analyzer is also like a polarized material, no? Just to analyze the intensity of the light which is going to get after completion of reflection with the help of analyzer. With the help of analyzer, okay? Suppose, for example, if the transmitted intensity will be 0 when the axis of the analyzer is in the plane of the figure, that is the plane of the incidence, right? So here he is explaining some sort of experiment, right? So how can we observe and what will happen with the help of analyzer to the reflected ray of light? Here reflected wave of light, because it is in wave optics, no? So we are taking wave picture of light. Next, after completion of that, when unpolarized light is incident on the boundary between two transparent media, the reflected light is polarized with its electric field vector perpendicular, right? Perpendicular to the plane of the incidence when the refracted and reflected rays make a right angle with each other. The sentence already repeated in our, that is what, just before 2 minutes, but once again he is saying which links with the angle between reflected ray and refracted ray. That is what, 90 degrees in this situation. Okay, I will repeat once again this important point. When unpolarized light is incident on the boundary between two transparent media, the reflected light is polarized with its electric vector perpendicular to the plane of the incidence when the refracted and reflected rays make a right angle with each other. Right angle with each other, right? So this we have seen that when reflected wave is perpendicular to the refracted wave, the reflected wave is totally polarized wave. The reflected wave is totally polarized wave. Actually, the situation will be different. That is not our consideration here. Here the thing is, when the reflected wave is perpendicular to the refracted wave, there we are going to derive some sort of expression, that is what, refractive index in terms of Brewster's angle. That we will see now. See here. The angle of incidence in this case is called as Brewster's angle. So when this is Brewster's angle, this is also Brewster's angle according to the laws of reflection. That is what angle of incidence is equal to angle of reflection. And this is 90. And when this is 90, this is Brewster's angle, this is R, no, it is what, angle of refraction. Then this Brewster's angle plus angle of refraction is equal to 90 degrees. When this is 90, when this is 180, then automatically the sum of these two also equal to 90. Okay, see here. The angle of incidence in this case is called as Brewster's angle and is denoted by IB, right? We can see that IB is related to the refractive index of the denser medium, right? So this in our previous chapter, ray optics, there we discussed. So what is the angle of refraction and what is angle of incidence, right? And what is the relation, what is the second law of refraction? There are two laws for refraction. First law is incident ray, refracted ray and normal lie in the same plane. Second one is the ratio of sine of angle of incidence to the sine of angle of refraction is constant. That constant is termed as refractive index. So it depends upon the pair of media. That is what is rarer medium and what is denser medium. Here rarer medium is air and denser medium is water. And if we replace it with water, any other optical denser medium, the refractive index will be different, right? Okay. See this. Since we have mathematically IB plus R is equal to pi by 2, we get from Snell's law, right? So it is I, it is R, sin IB by sin R, that is equal to sin IB by sin pi by 2 minus IB. So it is what cos IB, then sin by cos is equal to tan. So finally it is tan IB. If you want to know angle of, that is what Brewster's angle, it is tan inverse of refractive index. Next, this is known as Brewster's law, right? Next, see this. For simplicity, we have discussed the scattering of this is what happened in our previous class, right? For simplicity, we have discussed the scattering of light by 90 degrees and reflection at the Brewster's angle. Try to understand the situation. And reflection at the Brewster's angle, right? In our previous class, scattering of light. Just once you recall the picture what I drew in the last class, right? So it is what it is like incident light and it is like scattered light, right? So it is what atmospheric molecule, unpolarized light is coming like this in this manner. Here we have dots and arrows, right? Then it is what scattering light, that is what scattered light. The angle between these two is 90 degrees, okay? It's different. So that's we already completed in the last class, but here he mentioned. For simplicity, we have discussed the scattering of light by 90 degrees and reflection at the Brewster's angle. In this special situation, one of the two perpendicular components of the electric field is 0. In this special situation, one of the two perpendicular components of the electric field is 0. You know very well from our previous topics, that is what magnetism and moving charges and magnetism, right? Electric field is a three-dimensional vector quantity. Electric field is a three-dimensional vector quantity. And from the chapter of electromagnetic wave, you know that electromagnetic wave is consisting of electric field and magnetic field. And this electric field and magnetic field are oscillating perpendicular to each other and also perpendicular to the direction of propagation of light, right? So these 2 points we have to keep in mind when I am talking about the components of electric field, right? See this. In this special situation, one of the two perpendicular components of the electric field is 0, right? Okay. But what about at other angles? What about at other angles? At other angles, both components are present, but one is stronger than the other. One is stronger than the other. There is no stable phase relationship between the two perpendicular components since these are derived from two perpendicular components of unpolarized beam, right? Please try to understand two different cases. One is according to the special situation what is happening, another one is at other angles what is happening, right? At other angles both components are present, but one is like what is that higher magnitude, right? One is stronger than the other. There is no stable phase relationship between the two perpendicular components. There is no stable phase relationship between the two perpendicular components since these are derived from two perpendicular components of an unpolarized beam. Unpolarized beam, right? Next, when such light is viewed through a rotating analyzer, it is what like experiment. So if you see the reflected light through analyzer, right? Not only reflected light, you can also see refracted and you can also see the scattered light, whatever it may be. But here, when such light is viewed, through a rotating analyzer, one sees a maximum and a minimum of intensity, but not complete darkness, complete darkness. Complete darkness means what? No light is coming out. Transmitted light is 0. Transmitted light, that is what the emergent light. So you can say that the emergent light is 0. Light is not transmitting through the Polaroid, as simple as such. Okay, right. But here in this situation, whatever the situation we are having, whatever the situation, we are in a discussion. Right? If you see the light through a rotating analyzer, one sees a maximum and a minimum of intensity, but not complete darkness. You just try to imagine the light is coming, right? So here, according to this situation, the light is coming. So here we have, suppose for example the light is coming, here we have analyzer. So this analyzer is going to rotate. For example, this is analyzer, means that is going to rotate like this. So when you are rotating at one moment, at one instant of time, that is what maximum intensity. And if you continue that rotation, the intensity will decreases and minimum, not 0, and minimum, and from that instant of time again light will increase. So you can see only the maximum and minimum of intensity, but not complete darkness. This kind of light is called as partially polarized. This kind of light is called as partially polarized. Next, see here, let us try to understand the situation when an unpolarized beam of light is incident at the Brewster's angle on an interface of the two media. Only part of light with electric field vector perpendicular to the plane of incidence will be reflected. Right? Will be reflected. Right? So what is happening? When an unpolarized beam of light is incident at the Brewster's angle on an interface of two media, only part of light with electric field vector perpendicular to the plane of incidence will be reflected. Perpendicular to the plane of incidence will be reflected. Right? Now, by using good polarizer, if we completely remove all the light with its electric field vector, that is what electric vector, perpendicular to the plane of incidence, and let this light be incident on the surface of the prism at Brewster's angle, then you observe no reflection and there will be total transmission of light. So a small modification, just with small modification, he is explaining what will happen. Right? Up to here it's okay. Only part of light with electric field vector perpendicular to the plane of incidence will be reflected. Okay. Now, by using a good polarizer, if we completely remove all the light with its electric vector perpendicular to the plane of incidence, let us imagine. Try to imagine. You have to imagine every point what I am saying here. Then only you will get it. Right? So it's over. Now, by using a good polarizer, if we completely remove all the light with its electric vector perpendicular to the plane of incidence, let this light be incident on the surface of the prism at Brewster's angle. You will then observe no reflection and there will be total transmission of light. That is what he is saying. Right? So this is all about polarization by reflection. Right? So I will repeat once again from starting onwards. You please be concentrate. Right? Here, this situation already we know in our previous chapter when light is going to incident. Right? So light is a form of invisible energy. Certain amount of light is going to reflect. Certain amount of light is going to refract. The situation is not new for us. But while discussing about polarization by reflection, we also consider one more situation. That is what the angle between reflected ray and refracted ray is 90 degrees. Okay? That is what he is saying. So in this picture, that the reflected ray the reflected light is linearly polarized perpendicular to the plane of the figure. Reflected light is linearly polarized perpendicular to the plane of the, this is the reflected light ma, so which is linearly polarized, that is also perpendicular to the plane of the board, plane of the board. Okay, this you can check by looking at the reflected light through an analyzer. The transmitted intensity will be 0 when the axis of the analyzer is in the plane of the figure, is in the plane of the figure, that is what plane of incidence, plane of incidence, right. So when this that is what a linearly polarized light is in the plane of perpendicular to the plane of the board, and then if you try to see this reflected light with the help of analyzer, right, with the help of analyzer, and by keeping the analyzer, by keeping the axis of the analyzer in the plane of the figure, that is what in the plane of incidence, you will not see any light. So that is what the transmitted intensity will be 0. The transmitted intensity will be 0, and as I already told you, the angle between these two is 90 degrees according to the situation what we are in a discussion. Then automatically the sum of these two angles also 90. When this is 90, this is also 90. It is what Brewster's angle means according to the laws of reflection. It is also Brewster's angle, and it is the angle of refraction, right. So you can say that is what mu is equal to sin I by sin r, that is what second law of refraction. So first law of refraction is incident ray, refracted ray and normal lie in the same plane. Second law of refraction is the ratio of sine of angle of incidence to the sine of angle of refraction is constant, is constant. So from that we are writing here, right. So it is nothing, it is as simple as such, Snell's law, right. Mu is equal to sin IB by sin R, sin IB by sin R. So mathematically sin IB by sin 90 minus IB, that is what cos IB will come. So sin IB by cos IB means it is tan IB, it is tan IB, right. And the angle of incidence at which the light is going to incident is simply termed as Brewster's angle, is termed as Brewster's angle, right. So that is the main thing here. Next after completion of that, so he is repeating what is the situation here, again he is repeating. See this, for simplicity we have discussed scattering of light by 90 degrees, what we discussed in our previous class. Now in this case, and reflection at the Brewster's angle, reflection at the Brewster's angle. In this special situation, one of the two perpendicular components of the electric field is 0, but at other angles it will not be 0, but other angles one of the component is going, one of the component will be stronger than the other. At the same time we have to keep in mind one point, that is what there is no stable phase relationship between the two perpendicular components, between the two perpendicular components, right. Since these are derived from two perpendicular components of unpolarized beam, that is what he is giving the reason. It is what the statement, it is the reason. Next, when such a light is viewed through a rotating analyzer, you can see a maximum and a minimum of intensity, but not complete darkness. This kind of light is said to be partially polarized. Okay, that is what he is saying. Next, let us try to understand the situation when an unpolarized beam of light is incident at the Brewster's angle on an interface of the two media. Only part of light with electric field vector perpendicular to the plane of the incidence will be reflected, right. Now by using a good polarizer, if we completely remove all the light with its electric field vector perpendicular to the plane of incidence and let this light be incident on the surface of prism at Brewster's angle, you cannot see, you will then observe no reflection, and there will be no total transmission of light. There will be, and there will be there will be total transmission of light, means only this is, right, not this one. Next, after completion of that, here we are going to see one small example problem related to this topic, right. That is what, observe carefully. Unpolarized light is I am going to explain first problem, then we will go for solution. See this, unpolarized light is incident on a plane glass surface. What should be the angle of incidence? Unpolarized light is incident on polarized light is incident on a plane glass surface. Full stop. What should be the angle of incidence so that the reflected and refracted rays are perpendicular to each other, right? So it is a mathematical treatment. You know that I plus R to be equal to pi by 2, we should have tan IB is equal to 1.5. Tan IB is equal to 1.5. So when tan IB is equal to 1.5, you can find IB, that is what tan inverse of 1.5. Tan inverse of 1.5, it will give you 57 degrees. This is the Brewster's angle for air to glass interface. This is the Brewster's angle for air to glass interface, right? So here, according to the situation, he is asking, what he is asking is, what should be the angle of incidence so that the reflected and refracted rays are perpendicular to each other, means that angle is 57 degrees. That angle is 57 degrees, right? So this is about the linked problem to the topic polarization by reflection. Polarization by reflection, right? So in this topic, actually what is reflection, what is refraction, you know very well, but here our viewpoint is wave theory of light. From wave theory point of view, we are in a discussion, right? That is the main important thing. After completion of that, here we consider one special situation, that is what the reflected ray is perpendicular to the refracted ray, and meanwhile what happens to the reflected light, what happens to the refracted light, that we discussed in our discussion, right? And that you can observe with the help of analyzer, and we also derived an expression, that is what in terms of refractive index and Brewster's angle, that is what mu is equal to tan IB, right? So in case of whether reflection or refraction, so how the light is going to refract, whether it is partially polarized or completely polarized, that also we discussed, right? So this is about complete chapter wave optics. So this is the last class from the chapter wave optics. So in our previous chapter ray optics, we discussed the reflection and refraction properties of light, and by assuming light is propagated from one point to another point in the form of wave, we focus to discuss all the things, that is what major important properties of light also, like interference and diffraction and polarization, right? So these and all we discussed from these two chapters, that is what ray optics and wave optics. So wholly it is what part of optics, right? And not only this, because reflection is one phenomena, refraction is one phenomena, and then interference, diffraction, polarization, not only this phenomena, right? We also have another, that is what next, for example, I will tell you what is the photoelectric effect. That is also one of the phenomena. So that phenomena and related to the things about light, we also will discuss in our future. That is our next chapter, that is dual nature of radiation and light, that we already discussed, okay? Right. Thank you.